Okay, I thank the organizers for putting together this wonderful workshop and discussion meeting, and also giving me the opportunity to come and visit this wonderful city. Okay, so I'll talk about the experimental aspect of topological surface states, and I'll start out with a brief, maybe 5-minute review of the basic properties of surface states, and then I'll go mostly into proximity effect, like magnetic proximity and superconducting proximity we have been studying recently. And if I have time, then I'll get into topological insulators beyond Kane-Meili theory, beyond the Z2 theory, and we have some experimental realizations of that. Okay, so let me start out thanking my students and collaborators. So it's a collective work of my students and postdocs, and much of what I'll be presenting is presenting here. The focus here are carried out by these 3 students, and we have a number of collaboration around the country and around the world, and samples are, of course, very important. And most of my recent samples are actually from outside Princeton, Penn State, and Purdue, Nitin Samarth, and they're mostly MBE samples. So, we are now looking at the microscopic details of these interfaces and heterostructures, especially in connection to this proximity effect. Okay, so I do a wide variety of things. It's not just topological insulators. My background is actually magnetism and superconductivity and other stuff. But what is interesting here is that this field is now moving in a way to connect to things I have been working on. So this is a wonderful merge of all that I have been doing for all these years. So it turns out whenever there is a new physics, you need new instruments, because the instruments you build, they're not necessarily optimized to study certain types of physics. So we're getting into new development. We're developing this hybrid spectrometer at Jadwin Hall in Princeton to combine high field vector STM with ARPS, which is the usual stuff I do, in this case with time of flight, and then connect it through an MBE chamber. So then the idea is that I can maintain registry by looking at STM, and then I know where I looked. Then I go to the case space and I look at that. And also field will allow me to look at the vortex physics in superconductors and possibly look for zero energy modes and other stuff. So this development is actually quite important, and it's designed to probe topological matter, various forms of effects beyond where we stand. Okay, so this is the brief overview that I'll first briefly review the Z2 TI and then quickly go into topological phase transition and superconductivity, magnetism, and some other new stuff. And of course, I always these questions what is the quality of the samples, but let me reassure you, because we are working in momentum space and with spin sensitivity, we're not affected by whether there is bulk carrier or not. So our focus is to probe the topology of this matter or material. So the difficulty with transport is that it's not that selective. So you don't have a way to you get a mixed signal. So in other words, if the quality of the samples improve further, and it is improving, we're not going to find anything new, because what we are finding, it's already probing the topological order, so we're not dependent on. So of course, making devices is you have to get the transport and in high quality material so that you can apply these exotic phenomena to other things. So let me clarify. That's a clarification. Okay, so you have the extensive lecture series on the theory of topological insulators. I'm not getting into that, except for this slide is that in the quantum Hall state, you apply a field, you break time reversal, you have edge states. These are chiral. And you can think of the quantum spin Hall state as two copies of the up and down. And then this is still, this is the original 2D topological insulator. This is the time-reversed version of the 2D topological insulator. And so, but what is exciting to me personally is that in this case, you can think of stacking the 2D state, but you cannot, there is no genuine 3D topological insulator. You'll get surface state, but they're not robust, they're not protected. But in this case, now you got rid of the magnetic field, so now you'll have robust surface states on all surfaces, and they're topologically robust, and then there is connection, there is the bulk boundary correspondence. So this is exactly what we are probing. In fact, we started out probing these materials through transport, and we moved to spectroscopy partly because of the theory, because the actual topological order, in fact, even according to theory, cannot be probed through transport. Because the surface transport of 3D topological insulator is not Z2 topologically quantized. Joel touched on that point. So it's not, the topological order is already experimentally established. It's not waiting for the materials to improve so that you can see transport. You'll not see any Z2 quantization because of that.
So you don't think that if somebody sees half quantum Hall effect, that's a big deal?
Yeah, but you don't see that through transport. You'll get channels. You have to do that spectroscopically. You have to do that through. Yeah, you have to do that through some sort of optical method. You cannot do that, the transport in the conventional way. Yeah, I'm saying that this is the idea that the Z2 topology has to come from spectroscopy. There's a widespread misconception. In fact, this is something I wanted to mention. These two review papers were actually written, published before the spin of quantum spin Hall effect was measured. Right? So topological order was well established and reviewed before the spin of quantum spin Hall effect was measured. So this is why let me get into that in a real sense. So the focus of this talk is how these images tell us about topological order and what is the effect of how proximity would modify that. So, of course, in the quantum Hall state, the topological quantum number is the Chern number. In the topological insulator case, there are subtle things because now in this case, they're like Chern parity. They're related to the parity of the wave function, and that generates these 4 invariants. And they're, if you like, although there's no broken symmetry, if you like, you can in some way call them topological order parameter. And how to measure them, as Shankar has mentioned, that one way to do that, look at the half-integer quantum Hall, which is equivalent to saying that there's magnitude electric quantization. But that will only tell us the first invariant. It will not tell us about the other invariants. So the approach we are taking have already demonstrated and reviewed that this spin-sensitive momentum resolve age bulk correspondence, it will just give you everything. So that's the approach, and we're using advanced version of Einstein's photoelectric effect in all different directions, like in spin resolved, time resolved, polarization resolved, and we can do pump probe, look at the dichroic signal and all that by combining. In other words, the main idea here is to probe all degrees of freedom of the electron on the surface and in the bulk. And then look at the data and read off this topological invariance. That's what the theory tells us to do. But however, we did not get, I don't come from a quantum Hall background, so I did not set up to do that. We were looking at bismuth-based materials because I was interested in the thermopower contrast with sodium cobalt oxide I was studying. It is a triangular lattice exotic superconductor. And then we found that this particular compound, we could not access the bulk states. They have such a robust surface state that it did not make much sense. Of course, Fu and Klein did not know that we were looking at that, But once their paper came out, so we had a straightforward interpretation that we are seeing protected surface state. That's why we could not annihilate out. But then we decided to look at the spin, because then it will become clear whether there is a Berry phase on the surface or not. Without that, we cannot identify the topological invariance. So in this case, so what we did is that when you look at the satellite pockets, we see that only at the Kramers point, time reversal invariant point, you get the polarization rotating tangential to the Fermi surface. In other cases, that is not the case, so you don't pick up a phase. So the interesting part, the contribution to the phase comes from the center, and if you look down in energy, it looks like there is some sort of crossing. You have to go even down below. And then you see that, so this is the only interesting part. So this compound already had a single Dirac cone, but it has additional states. So we were trying to think how to localize these states, because the other pockets are not protected. There is no Berry phase associated with those pockets. So this is the usual surface science trick. If you change the surface potential, you localize surface states. If they're not protected, and that's what we did. We were changing the composition in antimony. We see that at high antimony concentration, there's a single Dirac cone, and this surface is very similar to bismuth selenide. They're all thermoelectric, and that's how we found this single Dirac cone material. So it was connected to our earlier work. And of course, we shared these results with my friends at Stanford. So the experiment and theory paper appeared in the same issue, but our paper has earlier, smaller page number. So it was actually experimentally discovered. Okay, so then we want to see. So in the beginning, we just saw these chiral.
So I
Yeah.
to make sure I understand. I realize they're older papers, but I have not followed the subject
Yeah,
very
yeah.
closely. So you said that these experiments conclusively establish the existence of the spin texture?
Yeah.
You would say yes.
Yes. Yeah, that's what I'm showing in this slide.
I just want to make sure, and then I
Right.
agree that you are seeing something topological. You
Right.
said that it conclusively establishes a spin texture.
Yes. So the idea is that these materials come with Fermi level in the conduction band, and how do you know that if, this texture is invariant across the gap? It could change. Then it's not topological. It could open a gap, right?
That's not a spin texture.
Yeah, exactly.
That's what I meant.
Right. So then you have to either chemically dope the system or do something related to surface effective doping, and then lower the Fermi level across, and then measure the spin everywhere. And then as you go through the node, you'll see that the chirality in momentum space chirality is changing, and it's not developing gap anywhere. So that established that the surface states they carry pi Berry phase no matter where your chemical potential is in the gap.
And this was done.
This was done. Yes, this is in the Nature.
Already in the early papers.
Yeah. Okay. So then, what does it mean in a simple picture, the real space picture? That what we are seeing when you look at the spin polarization channel, that K plus has, I'm just calling it down polarization, and K minus is up. So physically, it means that the electron moving to the right is down polarization, and moving to the left is up. And that's all we have in the Brion zone on the surface. So I have half the degrees of freedom. So I have, so now in this case, I have a 2D electron gas with half the degrees of freedom, and there is nothing else. And without spin, it goes back to your question, I could not have told that whether we have half Dirac gas or the full Dirac gas, right? So then, and then now since there is time reversal symmetry, so the polarization and momentum are locked, there is no other way to go around it unless you magnetize the system. And it's more interesting that on the surface, so from this point of view, it will look like quantum spin Hall effect, right? On the edge, that is what happens. But in 3D topological insulator, you can see that this pair is moving You always have a pair in any direction, and there is no edge universality. So, in other words, in the 3D case, in the experimental sense, there is really no quantum spin Hall effect. So it's so this is the strong topological insulator, but you could have that in the weak when the invariants are weak invariants at 0. Then you could have so that would be the generalization of quantum spin Hall in 3 dimension. Okay, so let me. So then we did more and more of these texture measurements, and then you can see that if you take this half Dirac gas, consider the self-convolution of the Fermi surface, then you can clearly see the absence of backscattering. So the idea here is that you don't have since you have this pair, then this electron, and this is a cartoonistic view that there's no state for this, nothing available for it to go there, so there's no U-turn. And so this, on the 2D gas, you can see that in the quasi-particle interference, and that's what we have done with the STM group at Princeton. But this is, in this case, we are just using a material that has more surface states to prove it in a more general ground, so that when you consider the Fourier transform of the STM signal, you can see that there are missing peaks. So in other words, the interference is there's spin dependence to it, and the only way to connect RPES and STM consistently is to suppress backscattering. Okay, so far, so these are the topological aspect of this topological insulator, and then we also showed a number of other things that now the question is, that typical topological insulators, they're limited to low temperature, and so we were curious whether the surface states and their textures would survive up to room temperature, and this was a very exciting thing to see that as you raise temperature even up to 300 K, your texture survives. Of course, the spectra would get somewhat broadened out, but the polarization that the Berry phase would survive. So this is the demonstration that this topological order survives up to room temperature. So this is kind of very exotic from the point of view that this is a quantum Hall-like effect at 300 K, no magnetic field. So that so now it lifts restriction of many experimental restriction limitations. So then there's an enormous play that comes with it. So that's what I'm going to talk mostly for the rest of my talk. But you can manipulate these surface states under UHV. You cannot. It's not easy to do transport under UHV, but you can get your Fermi level in the gap and maintain that there and do all sorts of measurements under UHV, and for spectroscopy, that's fine. And so that's what we are doing. Now, one thing is that to get to the bulk boundary correspondence, yes.
What's the difference between what do you change between?
It's like effective gating. We're chemically gating the surface, so lowering the chemical potential, so that my chemical potential is inside the gap. So this corresponds to this one.
And you change the chemical potential by doping?
By doping on the surface. By chemical doping, only on the surface, not in the bulk. Yeah. Okay. NO2. Yeah, it turns out NO2 whole dopes this system, and potassium or alkaline other stuff, it will electron dope system. It depends, that part depends on the surface chemistry, and you can maintain that in UHV, that's fine. But you cannot do transport so easily. Yeah.
How deep do the dopants go?
I don't think it goes more than a nanometer. I mean, it's all within that level. Mostly stays on the surface. It's like adsorbed on the surface. Yeah. So you have to choose the dopants in a way that there is no chemical reaction with the surface. If there is chemical reaction, then the surface states get below the level, but they're still protected as long as your oxide layer is not topological. So then you have interface so that it's protected because the oxide layer would be Z2. It's not Z2 Ti. So yeah, there's interesting. Even in that chemistry, there's interesting topological physics to be worked out. So far we saw all these crazy things. Now we wanted to figure out, okay, how do I recover my good old band insulator? How is this connected to that? So this is what we did here. If you replace selenium by sulfur, then you are reducing spin-orbit coupling. So then you can get rid of the band inversion that has happened. So when the bands are not inverted, then your surface state should disappear. So that is another check, a check of bulk boundary correspondence, that you have changed the bulk topology, which leads to the disappearance of surface state. And that's exactly we see, but it's more dramatic than that. If you just track the spin, so when you have in selenium rich samples, you have this type of texture, but then as you cross this 50%, 50% is an accident. It did not have to happen at 50%. Then you see the double, these bands are now degenerate because your Fermi level is the conduction band, but then there's a clean gap here. The surface states have disappeared. So the conduction band energy is coming down, and valence band energy is coming up, and then when this inversion happens, then you get the surface states emerge. These are some more details of that. I'll skip that. I mean, unless there's question. So in other words, we can now look at the topological phase transition. So one thing we did not immediately realize that now, for the first time, when you are at the inversion point, you have a three-dimensional Dirac cone. So it would be the real 3D version of graphene. But in this case, it's degenerate. It's not textured. And now we have another paper coming out on that. So far, nobody has really found a real three-dimensional version of graphene. So by tuning topological insulator, you can find a three-dimensional. You have to go to the critical point. And there's even more surprise there. At the critical point, if you're not centrosymmetry, if you break inversion symmetry, then you can get the Weyl points. You have the Fermi arc. So this is not easy to realize in this system because this system has center of symmetry, but then we have some other system in mind where this can be realized. We're working on that.
But the disorder that comes with alloy.
Yeah, I mean, it's not going to be high mobility. The mobility is not going to be anywhere close to graphene, but it's just for demonstration that in principle, you could realize Weyl fermion and 3D version of graphene. And of course, if there is interest from chemistry and material science people, they can try to improve these materials.
And the number of Weyl fermions will be smaller.
Yeah. So in that case, they will connect through the bulk. The crossing will happen in the bulk. So it's like the whole bulk is like the boundary of a 4D system, right? So half of the arc on top, on the bottom surface, other half. So then cross through the bulk. So it has to be semi-metal. So it has to be realized at the critical point.
The number of, because in the other materials where they proposed, there are many Weyl. Yeah,
so the Ashwin's proposal, he has 24 Weyl points, but in our construction, we should have just one pair, right? So because we're conditioning the material that way. So another interesting thing about 3D topological insulators is that you have additional Chern number, like you have mirror Chern number that's tied to this chirality. I'll not get into that, but just remind you that experimentally we determine that because it will come. It will be important when we do study things that are beyond Z2, topological insulators beyond Z2. So they have unusual mirror Chern number. So in this case, the one we studied, it has -1. So this is tied to this additional momentum space mirror plane. So now this is going back to Shankar's question regarding are the samples improving? Here is the data. This is 2008. And then we have like orders of magnitude improvement. We have fairly insulating samples. In fact, it's more insulating than silicon at 4 Kelvin.
So
The catch is mobility is low. Yes. Oh, this is just resistivity, just regular, as a function of temperature. Yeah.
And the different line?
Oh, different line is different material. Sorry. So this is like bismuth telluride, and this is a modified material. So bismuth, tellurium, selenide. It's prepared in 2 different states, and all that. So
these are your standard bulk samples. None of this applying gate.
No, this is without applying gate, but right.
No
Yeah, it's yes. So in this case, the native BTS samples have Fermi level in the gap, but the catch here is that the present mobility is low. Mobility is like 3,000. So the mobility has to improve. Yes. Surface mobility. Yes. But if you look at the carrier density, it's actually if you consider like Molenkamp he's using this 100 nanometer film. So if you make a 100 nanometer film out of these materials, you actually get less carriers in principle. If you just take the carrier and scale it. So it would be actually more insulating than mercury telluride. But the advantage here, people are trying to do that. It takes time for MBE people to perfect and realize how to do this ternary material. But the advantage here is that the gap is 200 millivolt. It's not 10 millivolt in mercury telluride. So the high temperature stuff and the proximity effect and other things would be more enhanced. Yes.
How do you know the mobility? There is a 2 component.
He's fitting in this paper.
All right, no, I understand that.
Yeah.
So this is not. I don't want to be very particular, but I'm a transport person. This is a direct measurement of the 2D mobility. You have to do some fitting.
Some fitting, yes.
You have to assume there are 2 components, one bulk.
Right. Okay, so this is the development, the materials development. I'm not directly involved in materials development right now, but I'm building this MBE hybrid spectrometer. We'll get into MBE soon. Okay, so far let me take a perspective. So that's my review of the status of the field in 3D TI. So the interesting thing here is that now that with 3D TI we have it's far less restrictive. You can operate at high temperature, no magnetic field. Even in dirty crystals, you can see the topological protections. The surface states are there. You cleave it, it's just there. I mean, you cannot kill the surface state so easily. In fact, nobody has succeeded in killing the surface state. So even in dirty crystals, the spin polarization is still 50%. I have a paper coming out on that. So these are really, really protected stuff. So then, but that's not the most exciting thing to me. To me, the most exciting thing is that these materials, you can turn them into magnets and superconductors. So you can study the interplay of broken symmetry and topological order for the first time in a real way. In other words, you can get antiferromagnetic order if you put 20% manganese in bismuth telluride. We'll have a paper coming up on that. But in this talk, I'll focus on the ferromagnetic part. Where you put manganese, then you can look at the effect of magnetism and also separately superconductivity. So a number of groups, because of these aspects, a number of groups have been working on it. But none of this would have happened without identifying the surface states. I mean, we are involved in all of this, but there are many other groups that are working on it. And by now, what I can count is like there are more than 300 experimental papers on 3D surface state, understanding various. Almost all of condensed matter physics can be done on the surface of these 3D topological insulators. Okay, so I'll give you some examples of what we are doing specifically. Our focus is to look at the topological aspect. I'm not so much interested in the material aspect. So one thing we're trying to do, dope these crystals with magnetic impurities and then probing with resonant X-ray scattering. That goes back to my PhD thesis topic. Looking at this dichroic signal and looking at the surface magnetism. And then combining that technique with this Mott detection spin RPS to see what happens in the surface state texture. Since I'm short on time, I'll just go to the result in some way. So what we see is that the surface states open a gap when you have a perpendicular component on the surface, but it has to come from a layer beneath that. And then we can clearly see this 3D texture, and it develops this hedgehog type texture. So the texture is it looks like that if you look at the full data set, and this is the gap. So at high binding energy, there is a Dirac-Berry phase, but then as you go to low energy, it vanishes gradually. So the next thing I'll talk about is how we observe proximity, superconducting proximity effect. This result is unpublished.
What does manganese do? Does it replace, or it's staying on the top?
It's in some case, sometimes it even clusters. But what is interesting, no matter what it does, homogeneous or inhomogeneous, it generates, the surface states develop this thing, this texture. But there is a global net out-of-plane component. Now that you can see that your surface Fermi surface is spin polarized, there is a net moment. And so that's independent of how manganese is distributed in the sample. So then I'll take a minute to go to the superconducting proximity effect we observed. Let me just mention one thing, that we can place Fermi level in the gap in these magnetic crystals, and that's how we get this hedgehog pattern. But what is interesting is that if you can create a hedgehog and anti-hedgehog, then you can get this dissipation-less 1D channel. So that is interesting for interconnect type technology. I briefly mentioned how we are getting to Weyl fermion through these developments. And now let me get to superconductivity. Many of you know about this copper doped bismuth selenide, and it remains unclear what is the order parameter symmetry despite this observation of in-gap states by...
I disagree with you on that one. I think it's completely established elsewhere.
I see.
I think that there is no way out of the data from NIST.
Right. But they did not apply. Ashwin has a paper. He's claiming that to see that you have to do tilted field, not the straight field.
I realize that, and that experiment should be done. I'm not,
right.
But I'm saying I'm kind of convinced that that's
I have a question mark here that this is unsettled. So we are moving on to something else, not that. So there are a number of other candidates that have lower TC, so we need new technology to work out. But meanwhile, I decided to go back and look at the Foucault thing, but in a spectroscopic way. So how to observe this proximity effect in a spectroscopic way. So what we are doing is that we are looking at the niobium selenide, bismuth selenide interface. And I want to figure out spectroscopically what happens at the interface. Is there a proximity effect? When you do transport, you're blind. You don't know. It's also the same thing with spin Hall or other things. So you don't know the microscopics at the interface. So this is what we're getting into. What is the interface doing? Since I'm short on time, what I'm going to show really quick is that we can look at the interface state and tell you what is whether there is superconductivity and how much Cooper pair coherence is there. So this is, and then we can tell you that it's not just the bulk band superconductivity that is modified at the interface that's what is creating the proximity effect, but it is the Dirac band that is developing a gap. And so this is the advantage of momentum resolution in our technique. So we can focus at this, pick this particular K value and do a temperature dependence. We see a gap, and then the gap is disappearing. Coherence peak is disappearing, and that goes with TC. So in other words, because of momentum resolution, we can selectively probe which band has developed how much proximity gap. What is the Cooper pair coherence in that system? So this is very, very exciting. This is actually first time anybody has shown in all the literature, not just TI, that the interface, what is the interface, this resolve, the proximity, band resolved proximity in superconductivity.
Yeah. So
yes.
Is this an MBE sample or is this a...
This is MBE sample. Yeah. So this is very exciting. Let me get to that. So what we are doing here is we are growing a few quintuple layer. Instead of growing a superconductor on top of the TI, we're growing the TI on top of the superconductor. It turns out that that's easier. And for us to be able to access the interface, we have to figure out how many quintuple layers we can afford to tolerate before the signal disappears, because we cannot look at the bulk interface, right? Because our technique is surface sensitive. So we see that up to 6 quintuple layer, we can look at the interface. It's it's something like that. So then, of course, the signal will be broadened, but at least we have the momentum. So the Fermi surface of niobium selenide has high momentum pockets, right? The Fermi surface of bismuth selenide surface state and the niobium selenide surface, they don't overlap in momentum space. So I can identify band-wise where is this proximity is happening, and that's what we found, that it is possible to realize this Foucault thing. So next thing is what Shankar would like to see is that when we apply magnetic field, what happens? Is there a zero bias peak or any of that stuff? So for that we need again new technology, and that's what we are building. We're building this hybrid spectrometer in my lab where we combine this high field vector field STM where I can manipulate. So this is also to check Ashwin's idea that you have to do a tilted field experiment. Just the perpendicular field will not be enough. Also, I think Patrick Lee has similar idea. And then combine these things and grow these films in there and then just transfer. So that way we don't worry about contamination or other things. So this spectrometer is also designed in a way to optimize this topological physics in not just in that system, a wide variety of other new states of matter. Can I have just 1 minute? Okay, this is my last slide. So I wanted to convey the excitement that it's now, with the Z2 topological insulators, it's coming from discrete symmetry like TR invariance, right? So how about other discrete symmetries? The space group symmetry, that should also, you could do a topological classification out of that. So do those topological insulators exist? And this is what we showed recently, that not only they exist, the fact that they're related to crystalline symmetry, these surface states survive even in an alloy. So this is a remarkable thing. I did not believe Fu's proposal that it will, he did not talk about its robustness, protected by the fact that they have mirrors. You can see that it's elongated along the mirror line, and they're protected there.
You continue to have spin texture.
You have spin texture. I don't have time to show that, but discuss that. But we did spin texture, and this takes us to this mirror Chern number. In this case, mirror Chern number is -2. None of this physics is in the quantum spin Hall, right? Because it's totally different state.
Is this material connected with the Polish material also?
They looked at something similar, but this is we're looking. They looked at the lead selenide.
I remember what it is, but
yes, they are trying to do a temperature dependence.
Okay.
Yes, I cited them here.
I was not worrying about size. Just so it reminded me this lead.
Yes, so they're doing a temperature dependence because in that system the gap is small, so they can close the gap. In our case, we're doing a topological phase transition and show that its topological character. So this is sort of my summary slide. I showed Dirac spin. This is the topological order of 3D topological invariant system, and then I showed hedgehog magnet and proximity effect. Thank you.
Because caffeine is beckoning, and we had a lot of questions. I'll take one burning question, maybe. Silent option. Okay, Vijay.
So, you showed this gap opening up on the surface, the interface.
Yes.
Which interface are you looking at? Are you looking at the direct interface between the NB SE?
Yes, the direct interface. But we can, if for small, if your film is small, then you should also see the top surface is gap.
So the proximity.
No, we haven't shown that, but we should be able to do that. I guess that's what you're.
No, I was thinking that you should see the Dirac cone on the top surface and the gap thing in the bottom surface, because I wouldn't have expected the proximity to leak all the way to the top surface.
It's a very thin film.
Oh, very thin.
The challenge here is that you cannot be ultra thin, because to get the 3D TI, you also have to have the bulky thing. So there's a cutoff there. So we are at the cutoff. Yeah.
The organizer is controlling the schedule. He can ask that question.
Okay, very short question. The reason you used niobium selenide instead of any other SOF superconductor, is it because of the easy MB growth?
Yeah, the reason I'm a spectroscopist, so I want the Fermi surface of bismuth selenide and niobium selenide not overlap, because then I cannot use my uniqueness that I can momentum resolve the proximity effect, right? So that's the main reason.
Okay, so it doesn't. No, my point was whether any other SOF superconductor would have done.
Yeah, it should. In principle, Foucault proposal is that anything should do that. But I haven't done the next experiment, which I have to apply magnetic field. There is a zero mode and all that stuff Shankar likes to see. But by the way, for spectroscopic thing, you're not doing transport, so the leaking and other stuff, I can spectroscopically prove Majorana, there's no problem. But whether that can be used in devices or not, that's a different thing, and I'm not concerned with that. I'm just concerned with the physics, that it's like in some way cold atom thing, right? So you can prove something, you cannot build electronics out of cold atoms. So all of my work is like just focus on the physics, not materials. Yeah. Oh, thank you.
Discuss in your slide the pi geometric phase. Yeah. Kindly show me the slides. I have to ask.
Yes.